The beginning of this lecture is going to be very similar to a lecture I gave in Physics 113, and then we're going to connect it to some ideas from Physics 114, extraterrestrial life. So in 113, we talked about the speed of light, and the speed of light is often referred to as a universal speed limit. It's often said you cannot travel faster than the speed of light. Now, technically, the statement above is true, but a more accurate statement to make is light travels at the speed of causality, or another way of phrasing that is light travels at the speed of gravity. So, what do we mean by saying light travels at the speed of causality? In discussing this, I am going to claim that nature should not allow the existence of a paradox. Now, this is just my opinion on the matter. I'm not going to attempt to prove this statement, but it seems to me that suppose we were to conduct some experiment or observation and we think we have seen an example of a paradox. Well, I claim that one or more of the following then must be true. Perhaps we did some experiment and there were some underlying rules of physics that we have not yet discovered. So those underlying rules of physics are emphasized in our experiment, and we don't know the underlying rules by which nature works, so we can't explain the observation of that experiment. So it's not really that there's a paradox, there are just physics at play that we don't understand yet. Or perhaps we did an experiment or made some type of observation and we have not properly taken into account all the relevant physics. There was an example about 10 years ago where some scientists thought they discovered neutrinos, little tiny particles traveling faster than the speed of light. But subsequent follow up analysis revealed that some important aspects of their experiment were not taken into account. When you account for those factors, then it turns out neutrinos were not traveling faster than the speed of light. So again, there was no paradox, there were no new physics, it was just not, all the important physics were not properly taken into account. Or perhaps we did discover an example of the universe being inherently illogical. But to say nature allows the existence of a paradox, that's like saying nature is allowing A not to be equal to A. Now, to me, this is just too weird, and I can't imagine nature behaving in a manner like this. I think nature needs to have a certain logical rules, logical mechanisms by which it works. So I'm going to ignore this possibility. So if we say light travels at the speed of causality, what do we mean by this? Well, what is causality? So to think about causality, let's consider two events that are related and connected to each other. Let's consider in a football game, there is a really long touchdown pass that is thrown, and let's consider in a football game, the crowd goes wild. Now, very clearly, these two events are connected in a certain way. If you were in the stadium watching this game, you would say that the touchdown pass was thrown, and then you would say the crowd went crazy. What if you were not in the stadium? What if you were watching this game from some other location? Perhaps you were in a building downtown watching with binoculars, or maybe you were on Mars or the Andromeda Galaxy watching this game through a telescope. In all of those cases, you would still observe the same progression of events. The touchdown pass will be thrown and caught, and then the crowd would go the appropriate magnitude of nuts. You would never see the crowd cheer and then the touchdown pass be caught. Because before the touchdown pass is caught, it is possible that the receiver drops the ball, in which case the crowd would never have cheered. So we demand that no matter where you are located, you will always see the same progression of events. You will always see the touchdown pass be thrown, and then you will see the crowd go wild. And it doesn't matter where you are watching this game, no matter where you are in the universe, you'll always see the crowd's reaction occur after the touchdown pass is thrown. Observers could also potentially be moving as well. The people in the stadium were not moving, they were just in wherever their seats are located. But if you're watching from a blimp flying overhead, well, you are moving with respect to the location of the game. Maybe you're in a rocket ship traveling around some globular clusters in the Milky Way galaxy, you're moving somehow. You would still see the same progression of events if you are watching it. You would see the 51-yard touchdown pass, and then you would see the crowd go wild. So we are going to claim that it doesn't matter where you watch this game from. It also doesn't matter if you are moving as you're watching this game. We will demand that you must always observe the crowd's reaction after the touchdown pass is thrown. Now, this idea can be generalized. Let's suppose we have two events A and B. So if we require that event A can influence event B, so in this case, event A could be thought of as the touchdown pass, event B could be thought of as the crowd's reaction. If event A can influence event B, but event B cannot influence event A, it is possible to prove that there is a maximum possible speed for any moving object. And so we call this the speed of causality. In other words, if we always require that cause comes before effect from the point of view of every possible observer, no matter where you're watching, no matter how you're moving if you're watching, the universe will possess a maximum speed limit, and that is the speed of causality. Now, I am not going to attempt to actually prove this. This conclusion is not obvious, so don't worry if it's not clear why this is the case. If you're curious to see an academic paper where this is proven, here is a link to a paper that proves this result. Now, it turns out light travels at the speed of causality. So, the universe having a maximum speed limit is a consequence of requiring cause coming before effect. So, what does this mean in terms of trying to communicate with some intelligent alien civilizations? Well, if we're going to send a signal from the Earth to the moon, and we'll send that signal at the fastest possible speed, so we'll send that signal in the form of light. Well, it'll take almost 1.5 seconds for a beam of light to go from the Earth to the moon. If you want to send a signal from Earth to the sun and back, then it would take 8 minutes for that signal to go from the Earth to the sun, and then another 8 minutes for that signal to travel from the sun back to Earth. So the further away an object is, the longer it takes time for that signal to reach that object. And this limits our ability to transfer information. This limits our ability to communicate, to have some type of phone call where we ask questions and get answers. So to send a signal to the nearest star and receive a reply would take 8.6 years. If we were to discover aliens around the nearest star, 4.3 light years away, if we were to say, hello, how are you? It would take 4.3 years for that signal to travel from Earth to the aliens around the nearest star. And then for them to receive the signal and reply would take another 4.3 years back. So it would take 8.6 years round trip travel time just to get a reply to, hi, how are you? And to travel to the other side of the galaxy, depending where you're going could take over 50,000 years. So if we, for the sake of argument, suppose that we have been broadcasting radio and TV signals for about the last 100 years. It's been a little longer than that, but let's just use 100 years as a nice round number to work with. Then the very first radio broadcasts way back in the early 1900s have been moving away from the Earth at the speed of light, and those now are the furthest radio broadcasts that we sent out away from us. They're the furthest ones out in space. And more recent radio broadcasts have been traveling away from Earth, but they're not quite as far away from us because they didn't have as much time to travel out. Now, if we just assume as a rule of thumb that radio broadcasts are spreading out into the universe approximately evenly in all directions away from Earth, that would mean that our radio broadcasts are expanding away from the Earth in the shape of a sphere. So if you think about it, if we say the earliest radio broadcasts have been sent out 100 years ago, that would mean those very first radio broadcasts are now 100 light years away from us. And if we have radio broadcasts that are 100 light years away from us in all directions, that would put us at the center of a sphere. And compared to the size of our galaxy, our radio broadcasts have reached out very little into our galaxy. So we have a sphere that is 200 light years across with the Earth at the center, this tiny little blue dot right here. And compared to the size of our galaxy, the extent of human radio broadcasts is very minuscule. Now, there are good reasons to think, even if there are aliens within this very small sphere compared to the size of our galaxy, that the aliens would never receive our radio broadcasts. For one thing, radio broadcasts tend to decrease in strength as they spread out and dilute in the universe. Another thing, the radio broadcasts are intended to be picked up by receivers here on Earth. They're not intended to be picked up by aliens. So this was not a dedicated alien finding mission when we started broadcasting in radio. But the extent of our radio broadcasts are really small compared to the size of our galaxy as a whole. So let's suppose we wanted to undertake a dedicated contact with aliens. If we were looking for broadcasts from alien civilizations, what type of signal could we expect an intelligent civilization to emit? Now, we are limited in what we know. We really have no clue on what alien psychology would be like, but just for the sake of argument, due to the lack of any better idea, let's assume that aliens will send signals with light. Now, as I said before, light travels at a certain speed. We are not able to get around this restriction. To get around this restriction, you would need to live in a universe where cause could come after effect, and that seems like an inherently illogical universe, so we are restricted by the speed of light. Now, when I say aliens are going to send signals with light, I don't necessarily mean visible light. There are many colors of light that we cannot see with our eyes. Radio is one example of a color of light that our eyes cannot detect. Same with infrared, gamma rays, X-rays, ultraviolet. These are just different colors of light at different wavelengths that are just not detectable by the cells that make up our eyes that see light. So there are a lot of possible different wavelengths, a lot of possible different colors of light that aliens could broadcast or send signals in. Which wavelengths of light should we be looking at? Well, for one thing, many wavelengths of light, many different colors are blocked by our atmosphere. So you could ask the question, with limited science funding, is it worth it to dedicate a space-based mission to search for extraterrestrial intelligence that could look at all different colors of light? If you want to look for aliens that are broadcasting in UV or X-ray light, you need to go above the atmosphere, and that would significantly increase the cost of a science experiment looking for aliens. On the other hand, short wavelengths of light, like your radio and your microwaves, those short wavelengths of light are very low energy colors of light. And so you could ask the question, even though we really don't know how aliens think, how their psychology and sociology would be, is it reasonable to expect aliens would be more economical if given the choice in how they send out signals? Why would aliens send out a very expensive signal, a high energy signal, when they could send out a cheap signal, like a low energy signal? So why would aliens expend more resources to transmit a high energy signal when they could use fewer resources to transmit a low energy signal? Okay, this seems reasonable. So maybe we can search for aliens with telescopes that are based on Earth, that are dedicated to looking in the radio and the microwave part of the electromagnetic spectrum. Well, even within radio and microwaves, there are a lot of possible different wavelengths of light, a lot of possible different colors of light to be looking within radio and microwave. So what color should we be looking in? Can we narrow it down further? Well, light with wavelengths longer than 30 centimeters tend to get mixed up with the natural background from our galaxy. So here, the horizontal side of this plot is frequency, so the long wavelength is actually on the left side of this plot. And if you have a wavelength longer than 30 centimeters, then you're going to get lost in a lot of the background stars and nebula and other stuff going on in the galaxy. So your signal is going to be drowned out by all the light just naturally emitted from objects in the galaxy. If you have a very short wavelength of light, less than 1 centimeter, you're going to be absorbed by the Earth's atmosphere. So unless we want to spend money to actually go and put a telescope into space to look for these radio signals, we're stuck on Earth. The Earth's atmosphere is fairly transparent between 1 centimeter and 30 centimeter wavelength range. So this is all in the radio region of the electromagnetic spectrum. And even within this range, there is still a lot of possible light to investigate. So where are we going to look for signals of alien radio waves? Well, atoms and molecules absorb and emit light at very certain specific wavelengths, at very specific colors. This is spectroscopy that I talked about at the beginning of PHY 113. And these colors indicate what type of atom you're looking at. Essentially, the colors that these atoms and molecules absorb and emit are the fingerprint of those atoms and molecules. So this topic is not really going to be covered in this course, but it is very important in astronomy. It was discussed earlier in some of the PHY 113 lectures in the background science material. And let us presume that intelligent aliens know of water. So if you're an intelligent alien, if you're interested in science, then you probably know of the existence of water, because water is all over the universe and water is probably necessary for life. So the OH, the oxygen hydrogen molecule, emits light at a very specific 18 centimeter wavelength. Hydrogen emits light at a 21 centimeter wavelength. And if aliens are aware of the necessity and importance of water to life, then we could say maybe between 18 and 21 centimeters, there give H plus HO gives H2O. That could be a region to look for alien radio broadcasts. It is possible that there are alien radio broadcasts elsewhere in the universe, but this is possibly a promising region of the electromagnetic spectrum to look for alien broadcasts. So there are many possible different colors. There are many possible wavelengths of light to look for alien radio signals. But without anything better to go on, it might be possible to narrow it down somewhat. If aliens are trying to announce their presence to anyone who might be listening, such as us, then they will, if they're trying to be found, then they will probably be asking a question like, what wavelength of light will make me the most visible? And other intelligent species know of the existence of water, then water might be an important benchmark to broadcast at certain wavelengths around the water hole. For a short time, the US government funded SETI, the Search for Extraterrestrial Intelligence. SETI was a survey of the sky looking in radio frequencies, just searching for evidence of aliens trying to send out radio signals and communicate. Funding for SETI was cut by the US Congress in the early 90s, but since then SETI has continued through private funding and its name has been changed to a more supervillain-esque name, Project Phoenix. And in the search for extraterrestrial intelligence, you can help. If you go to SETI at Home and download their screensaver, what SETI at Home is there is a lot of data collected by radio telescopes, but there is not that much computing power available compared to the amount of data collected. So if you go download the SETI at Home screensaver, anytime your computer goes to sleep or into a screensaver mode, a little bit of data that is collected by a radio telescope will be sent to your computer, and then your computer's processing power will analyze that data, send it back to SETI's main website, and from there your computer can help in the search for extraterrestrial intelligence.